So our first talk this morning is Alex Scott, who will continue on the line that Jason Brown and Roberto Fernandez started in previous days about the independent set polynomial.
Okay, thanks. So the first thing I should say is that everything I'm talking about is joint work with Alan. Okay, of course, the theme of this whole meeting is combinatorics and statistical mechanics, and there are often sort of surprising connections and meeting points for the two. And what I'm going to talk about is a connection between results in combinatorics and statistical mechanics that Alan and I found a few years ago. Okay, so the talk really comes in three pieces. So there's a bit where I'll talk about something in combinatorics. There's a bit where I'll talk about something from statistical mechanics. And the two will appear to be completely disjoint. And then there's a third part of the talk where I'll talk about what the connection is between the two. Okay, I'm not going to assume anything, so I may find myself, you may find I'm repeating things you've heard earlier in the week or things that are already very familiar to you. I'm aware they're both physicists and combinatorialists here, so probably I'll bore at least, well, I'll probably bore everybody at least half the time, but hopefully I'll interest everyone at least some proportion of the time. Okay, so let's start with the combinatorial problem. Okay, so in probabilistic combinatorics, you're often in a situation where, so you have some probability space, and some events in that space, and these events are bad events, so you don't want them to happen. Okay, so you have events for A1 up to AN, say, and you like some bound on the probability that none of them happen. Okay, so, right, well, there's a trivial bound. I mean, the probability that one of them happens is at most, or any of them happen is at most the sum of the probabilities. So here is your trivial bound on the probability that none of them happen. Okay, trivial and okay, sometimes useful, but often completely useless because this is too big. Okay, so the next thing you can say, well, okay, if they're independent, I know exactly what the probability that none of them occur is. Just the product of the individual probabilities. Okay, so again, you can answer it, but life isn't usually that nice. Usually there's some dependence floating around. And then that's when things get interesting, because then you have to start sort of thinking and say, well, how am I going to control it? Okay, well, one natural way of doing this is via a dependency graph. And so the idea here is we have some graph. So some of the events will be dependent, not all of them will be dependent. There'll be a certain amount of dependence floating around. Okay, so there'll be some, let's say there's some structure like that, and each vertex here corresponds to one of your events. And the idea is, okay, so informally, the idea is that you join events that are dependent and you don't join them if they're not dependent. Now, of course, that doesn't actually encapsulate what dependence is like, because dependence is a more complicated beast. So we'll at least just demand that you can control dependence by this. So what I mean by that is, if I take an event, it will be independent from the events that are not adjacent to it. Okay, so this event is independent from those events, more precisely from the sigma algebra they generate. Okay, actually I'm going to have some transparencies as well. So my thought was that I'd sort of put the Cliff's Notes versions up here, and then kind of the seminar happens over here. But this is just sort of a summary of what I'm talking about. Okay, so here then's the formal notion of a dependency graph. It should be that every event is independent from the collection of events that is not adjacent to it. Okay, so let me kind of just raise a slight caution here. So dependency graphs aren't always sort of uniquely specified by the events. Okay, so one thing is I could always just add an edge, and if it was a dependency graph before, it's a dependency graph afterwards. But it's also the case that even kind of minimal dependency graphs aren't given to you by the events. So the sort of standard example would be you take a collection of n coins, so or n 0, 1 variables, okay, n coins, and you condition on an even number coming up heads. Okay, and otherwise heads, tails, equally probable, independent. Right, so clearly that full collection is not independent, but any subset of n minus 1 forms an independent collection of events. Okay, so for this collection of events, the possible dependency graphs are any graph with minimal degree at least 1. So any graph G with minimal degree at least 1 is a dependency graph. Okay, so it isn't necessarily uniquely defined. On the other hand, often your events come from some underlying collection of events. So often each of these refers to some underlying set of random variables. And in that case, there is a very natural dependency graph. You join two events if they share a random variable. Okay, so usually there is some natural dependency graph that pushes itself upon you. Okay, so with this context, with this notion of dependency graph, the natural question is, well, under what conditions, and by that I mean how large can the probabilities of these bad events be, and we can still guarantee that none of them happen with positive probability. Okay, ideally you'd like a bound on that probability as well, but non-zero probability is usually what you're after. Okay, so you have this general question up here. So suppose you have a dependency graph G, and for this talk my graphs will always be called G. So I'll just say X will always be the vertex set of G, and N will always be the number of vertices in the graph if it isn't something else. So okay, so the general question then is, given a dependency graph, when can we guarantee the probability that none of our events happen? In particular, what bounds will suffice on the individual probabilities to guarantee that none of them happen with positive probability? Okay, so we'll allow a different bound on the probability for each event. Okay. Right, so there's a very nice theorem that works in this context. So I should have said, before I take that off, so we'll say that a sequence of probabilities is good, or sequence of real numbers is good, so a sequence of real numbers is good if bounding the probability of events by px is enough to imply the conclusion that we want. So if that implies probability that none of the events happens is greater than 0. So that's a good sequence. Okay. Right, so natural question, what sequences are, oops, going the wrong way. Okay, so a very nice result, the Loavsz Local Lemma, gives one criterion for a sequence to be good. So let me emphasize this is it's an extremely useful, important theorem. It's a sufficient but not necessary criterion. Okay, and it gives some criterion that the details don't matter too much at the moment. It just says if you can bound the probabilities by some appropriate numbers, then probability that none of your events happen is positive. Okay, now The natural question then is how good is the local lemma? And is it close to optimal? And there's again a nice result of Shearer. So he gave bounds that were, I've been slightly unfair to him here. So he gives bounds that are asymptotically optimal for regular trees. Okay, so what he actually showed was that if the maximal degree of G is delta, then the sequence where we take Px to be, let's forget which is the delta and which is the delta plus 1. Yeah, there you are. Delta minus 1 to the delta minus 1 over delta to the delta is good. Okay, so he said he gave a bound on good sequences in terms of maximal degree, or a sufficient criterion. Okay, but he also showed that if you take a delta minus 1 branching tree, then as you take a larger and larger tree, this is asymptotically optimal as well. Okay, so it's the best possible bound in terms of maximum degree. Okay, as delta gets large, that's 1 over E times delta. Okay, so some constant over delta is roughly what you'd expect if you think about it for a bit, because it's the number of edges you have coming out. If you think about the complete graph, that tells you pretty quickly your bound has to be a form constant over delta. Okay, so this bound is optimal for trees. Okay, but what about for other graphs? So, I mean, trees are very sparse, and that's why you can do the optimality analysis. What if you have a denser graph? So, I think maybe it's useful to think about just a diagonal case. So, I'll write R of G for sup of P such that just the constant sequence P is good. Okay, so just a uniform bound, in other words. Okay, so Shearer showed that if maximal degree is delta, then R of G is greater or equal to delta minus 1 to delta minus 1 over delta to the delta. Okay, but if you have a more complicated graph, so for instance, big piece of the square lattice, then what can you say? So certainly this will give you whatever it is, 27 over 256 bound. But what is actually the correct optimal value here? And it's completely unclear, at least at first glance, how you might go about calculating that. Okay, so that's the local lemma. And that's good sequences. So let me emphasize again, the local lemma gives a useful criterion. It's not optimal, so there are kind of regions that it doesn't cover.
So gamma of x is those vertices adjacent to x, right?
Yes, it is.
That's why it's local.
Yes, so the point is it gives local because it's giving a bound in terms of the degrees of the vertices. So in terms of how yeah. That's clear.
Excuse me.
Yeah.
I'm too late to concentrate myself. If you, instead of using Scherer's optimal result, use the Loavsz Local Lemma for just knowing the maximum degree, how far off will you get?
I forget because sometimes I did the calculation. I think it's delta becomes delta plus 1. So,
Okay, so it's pretty close.
but with a sort of warning, I'd have to check it. Yeah. Okay. It's an easy check. Okay. So, having bored the combinatorialists, let me have an opportunity to bore the physicists. Okay, statistical mechanics on graphs. So now we're into the statistical mechanics part. So we're going to work with a sort of very simple setup. So Okay, I probably don't need to repeat any of this, but anyway, so we're working just with graph colorings. And the idea is we have some finite set S that we're using to color the graph, and we can color each vertex as we wish. But then there's some score that tells us, well, the energy of called the Hamiltonian, tells us the energy of a configuration, or just the weight of any given coloring of the graph. Okay, and something that comes out of the physics says you want to make the probability of being in a particular state, in other words, the probability of getting a particular coloring, to be proportional to, well, e to the minus beta times h. And beta is just some constant that you're given, called the inverse temperature. Maybe the one thing to point out is that, well, inverse temperature means it's sort of 1 over temperature. So if the temperature is large, that means beta is close to 0, and you're getting close to a uniform coloring. So just coloring the vertices independently. If the temperature is small, in other words, beta is large, then configurations for which h is small, or low energy configurations, are favoured, and as the temperature tends to 0, then you're focusing on minimal energy states. So you end up with combinatorial problems such as max cut or optimal colouring or whatever. Okay, so the crucial thing here turns out to be, well, the normalizing constant. It's the thing that, again, you define this and you think, oh, the normalizing constant's just unimportant. But it turns out to be the subject of a lot of interest. And maybe I'll just say lots of information could be read off looking at this normalizing factor. So it's called the partition function. I'm very aware I'm repeating things that everyone else has said, so I'll go quickly. So that's going to be our subject our topic of concern. Okay, so let me sort of jump immediately to talking about the model we're going to talk about, and we're talking about the very simple and very nice lattice gas model. Okay, so I'm going to define this first in something called the hardcore context, and I'm going to gesture at ways you can generalize it. Okay, so in fact I'm going to annoy Alan by defining it in the univariate form first. Okay, so we have the sort of simplest possible idea. So you have some graph G, and the idea is that you're sort of plonking molecules or atoms or whatever they are down on the sites of the vertices of the graph, and they violently dislike each other, so you're not allowed to put them adjacent to each other. Okay, and what's your measure of energy? It's the simplest possible thing. You're just counting the number of occupied sites. Okay, so here we have the legal configuration then is just an independent. I don't think I said independent. Oh no, I did. Okay, an independent subset of the graph. So legal configurations are independent sets, and the weight of an independent set is just the number of vertices. Okay, now so. So the partition function is the sum over independent sets, e to minus beta times the size of the independent set. Okay, so the nice thing here is that although you've started out with something involving e to the minus betas, you can just turn it into a very pleasant polynomial by writing a new variable for e to the minus beta. So let's write z for e to the minus beta, and this is sum over I independent e to the z to the mod I. Okay, so we're straight back to something very graph theoretical, and familiar, the independent set polynomial. Okay.
What beta is?
Sorry?
What beta stands for?
Beta is the inverse temperature. But again, I'm deliberately presenting this somehow as a kind of purely combinatorial thing, and I'm sort of ignoring the physics. So it's some constant that's given to us by the setup. Okay, so that's
e to the minus beta. That's the minus sign.
In the other equation.
The far
oh, so yes, there's thank you. There's a minus sign there. Yeah. Okay, so I want to emphasize you can think of this just purely from a combinatorial perspective. Of course, you then have the physical perspective as well, which gives you a different view. Okay, so you have the independent set polynomial. Right. Now, at this point I should say, well, yes, the univariate independent set polynomials very nice, but actually you gain a huge amount by generalizing this a bit and allowing a different variable for each vertex. Okay, and there are really two reasons, that's essentially the same reason. So one is that if you allow a different variable for each vertex, then rather than a complicated polynomial here, you have something that's multi-affine. It's a degree 1 in each variable separately. And as I'm sure other people have talked about, that gives you some great analytic advantages. And the other thing is that by having a multivariate version, you can decouple the effects of different vertices. Okay, and so you can think about different parts of the graph more easily. Okay. Right, so it's just a small modification. So rather than z to the I, you end up with, well, actually I have it written up here. So you just have a different variable for each vertex of the graph, and the multivariate independent set polynomial is sum over independent sets, and for each independent set, the weight is product over elements of the set of the variable associated to those vertices. Okay. Okay, maybe a couple of things to point out about this, though. So one is to say, just in terms of names, this thing, little z, is called the fugacity. From the way we've come at it, so it came out of e to the minus beta mod I. Everything here is real at the moment. I mean, we're going to move into the complex plane in a minute. But since this is real, this tells us that z should be a positive real number. Okay, so sort of the initial domain of physical interest then is positive reals for this. Okay, so in particular, we have a polynomial with positive real variables and all coefficients positive. So it's going to be positive. Okay. Maybe another thing to say is, and you can start writing out the independent set polynomial. So the empty set is independent. So z is of the form 1 plus, okay, what's next? Single element independent sets. Okay, so sum over variables of x, zx plus, okay, and then two variables and so on. Okay, so it's 1 plus something. However, calculating the independent set polynomial is non-trivial. Even working out the degree of the independent set polynomial is NP hard because you have to work out maximum size of an independent set. Okay, so computational issues are likely to be non-trivial here. Okay, so what do we want from our independent set polynomials? So again, I'll skip over this mostly, but I'll just say that we want to know about phase transitions. And a phase transition is where you have some point where your function is, so at least in kind of pure mathematical terms, where your function is non-differentiable or discontinuous, or there's some, it's only 6 times differentiable, not 7 times differentiable, or it's not analytic. It's badly behaved in some analytic way. Okay, now it turns out that a lot of the information you want comes from looking at log of the partition function rather than the partition function itself. And points where log is badly behaved, well, certainly zeros of z are going to be those points. Okay, so we're interested in zeros of the partition function. Okay, but hold on, I just pointed out that our partition function has no zeros. Okay, at least not in the positive reals. Okay, so what's going to happen? Well, in general, we're going to be interested in, rather than just one graph, limits of sequences of graphs. So we might be interested in a big piece of the well, we might be interested in the whole plane, so there's a whole square lattice in the plane. So we think of that as a limit of pieces of larger and larger pieces of the square lattice. Okay, so there's some stuff you have to do to prove things, but under kind of reasonable conditions, you can prove statements about limits. And what happens is that, okay, I'm giving a very abbreviated version of this. Okay, so let's think about the specific example where you take larger and larger pieces of the square lattice. Okay, as you look at log of the partition function and maybe some normalized version of it so you get something that converges, you're going to get a sequence of analytic functions. Okay, and modulo doing some work, these converge uniformly. Okay, well, what happens to the zeros of those? So, I mean, initially we had no real zeros at all, no positive real zeros at all. Okay, but it turns out that as you take larger and larger pieces of the lattice, the zeros approach the real axis. And so even though they're never actually on the real axis, in the limit you're getting some sort of bad behavior on the real axis itself. Okay, so that's a very kind of sketchy, quick version of that. But what it says is that the location of zeros in the complex plane is important. Okay, so if we can tell where the zeros are, and also we can show that limits behave in the way they should, or that we'd like them to, so modulo doing some proof, you can show that, well, there are regions where phase transitions don't happen in this case. So generally what we're going to be interested in is showing that there's some region where our functions have no zeros, so sort of everything's analytic inside, and you can use that then to show that in the limit you get no phase transitions. Okay, so since there are no zeros, there's no way of pinching the axis. You have to show some things about uniform convergence and invoke a little bit of complex analysis, but the main point is finding the locations of the zeros. Okay, so theorems that say there are no zeros in certain domains are known as Li-Yang theorems, and that's where this sort of whole story comes from, in sort of very abbreviated way I've given that. Okay. Right. So then there's a natural general question. What regions of the complex plane are free from zeros of the multivariate independent set polynomial? Okay, so here's then the general question. Since it's multivariate, it's sensible to allow each variable to range independently. And since the polynomial has this form, well, a good candidate for a region will be some disk around the origin. Okay, we know it's non-zero at the origin itself. We know it takes value 1 at 0. So let's look at what happens in some disk. Well, some polydisk, because each variable is independent. Okay, so what we'd like is to have a sequence of reals, Rx, so one for each vertex, that says if each vertex, the variable is constrained to lie in the disk of radius r around the origin, then we can guarantee there are no zeros. Okay, so that then's the question. And again, there's a nice theorem due to de Bruijn that gives a sufficient but not necessary condition to be zero-free. And again, it gives, just as in the Loavsz Local Lemma, it gives some essentially numerical bounds on what you could hope for. Okay, again, let me say that I'll call a sequence good if the corresponding polydisk has no zeros of Z. Okay, so notion of good here as well. Okay, now the way I've written this is I hope slightly suggestive, because I've kind of written them in a parallel way. But I mean, it's not at all obvious that de Bruijn's theorem and the Loavsz Local Lemma, or these two problems even, are connected. Okay, but The surprising thing is it turns out that they are connected and very closely connected. Okay, so now on to the third part of the talk, which is connection.
Maybe you want to first rewrite de Bruchen's criterion in slightly different variables?
No, I don't.
Oh, no, okay.
I'm trying to avoid going through the sort of estimates themselves. I'm just sort of saying
No,
that.
I just meant that if you make a slight change of variables in de Bruchen's.
No, don't say that. Don't say that. It's at the bottom of the slide. Okay, so here's the surprising thing. The two problems that I've talked about, when is a sequence good for the dependency graph in the dependency graph context, and when is a sequence good in the lattice gas context, they turn out to be exactly the same problem. By which I mean a sequence is good in one context if and only if it's good in the other. Okay, so a sequence of reals is good for the dependency graph G if and only if the complex polydisk with those radii contains no zeros of the partition function, of the same graph, of course. Okay, so the two problems are actually the same. Now, of course, as soon as you find that the two problems are the same, and you have two communities that have looked at the problem, you say, well, how do the results compare? Is Loavsz going to beat out de Bruchen, or is it going to be the other way around? Okay, so of course we immediately sort of thought, how do they compare? Which is better? They're exactly the same. So the local lemma and de Bruchen's theorem give exactly the same bounds, and it's actually just, as Alan pointed out, it's a simple change of variables to get from one to the other. Okay. Now, when I say it's a simple change of variables, what I mean is, if you assume theorem 3, so if you assume that the two problems are the same, then you find out you get the same numerical criteria from the two results. Okay, so let me think of just a second. Okay, so I think most of the rest of the talk I'm going to try and give some idea of how you prove the connection. Let me emphasize that both the local lemma and de Bruchen's theorem are not optimal results in the sense that they give sufficient but not necessary criteria. So you can still hope that you'll be able to move results backwards and forwards between the two problems. So if you prove in some context an improvement on the local lemma, you can take it straight across and use it in the other context. If you prove something about zeros of lattice gases in an appropriate context, then you can bring it back into the dependency graph. In particular, if you're looking at something like a big piece of the square lattice, you could hope that statistical physicists will be able to tell you something about that and then bring it back to the original context. So I'll mention that briefly at the end. And I'll also mention briefly something about what happens when, rather than working in a hardcore context, where you have sort of strictly forbidden things, you soften everything. So you can do that as well. Okay, but let me talk at least briefly about the proof. Okay, so the proof of theorem 3. Okay, and this is one of those proofs where you start from either end and it meets in the middle. So let's maybe start first with the lattice gas context. Okay, so we have Z is sum over I independent, product over X and I ZX. Okay, so the first thing is, I'll work in terms of W's. So this is Z of a vector W. Okay, so the first thing to say is, rather than having to sum over independent sets, which are a bit tricky to handle, let's write this in a slightly different way. So let's introduce something called WXY. So this is the Boltzmann factor, yes. So wxy is going to determine the tolerance between x and y. So it's going to be 0 if xy is an edge, 1 if xy is not an edge, and actually I'll allow x to be equal to y. Okay, that's not quite. So in the first two cases, x is not equal to y. In the third case, if x is equal to y, then you give it weight 0. Okay, so this is in some sense the complement of the adjacency matrix. So in the adjacency matrix, you have 1 if two vertices are adjacent and 0 if they're not. Here it's the other way around, so it measures tolerance. Okay, and on the diagonal we've done something special. Okay, so the advantage of introducing this factor is rather than a summing over independent sets, you can now just write it as the sum over all subsets of x, product. Okay, so there's a product over x and s wx, and a product over pairs w x y. Separate. Okay, and all this does is if your set is independent, then all the wxy's are 1, and so you keep the factor. If the set is not independent, there'll be an edge in it somewhere. Wxy will be 0 for that edge, and it just wipes out that term. Okay, so this is just a more convenient way of writing it. Okay, now it also has the advantage that you can see how you might generalize it, because this wxy, well, here we're constraining it to be 0 or 1. You could allow a soft interaction, so you'd allow something between 0 and 1. Okay.
Also not between 0 and 1.
So it could
Also not between 0 and 1.
Yeah, you could also extend it beyond that.
If you stay between 0 and 1, you are repulsive.
Yes, okay.
Yeah.
Yeah. Okay, I didn't want to generalize it too far. So.
Can you say again what's the condition for xy here? The subs, the members or in S?
Yeah, so I want it to be a product over all pairs. So this is all pairs x, sorry, subset. That should have been subset.
And then here you must be careful because y always can be x. Y equal to x ws by 0. And then here you don't need to define x equal to y.
Yes.
What, here you mean?
Yes, you don't need x equal y equals 0 if you do that.
Yes.
Yeah,
You don't
it's
need
not
to
necessary.
define
Oh, yeah,
it for
no,
every
I-
point at this point.
It's not for this point, it's
Yeah, it's not, you don't need to define x equal y.
it's just convenient to write that down now. It's allowed. Yes, and I want to keep everything positive. I want everything to, between 0 and 1, I want it to be repulsive, so I don't, yeah. Okay. For this discussion, I'll just keep it as 0 and 1 for simplicity. So keep it in the hardcore case. Softening it actually is not significantly more difficult. I mean, it's just you carry these factors through and it works. So, okay. Right. Okay. So I'm gonna mess around with this in a minute. Maybe I should first say where we're going. So.
I think here it's not quite right because you take every S, so some content you repeat. Because for every S, for every pair,
You take the product over all two element subsets of S,
No, it's okay.
and then it's okay.
It's okay.
Yeah, I was trying to write it informally, and that turned out to be a bad idea. Yeah.
Actually, there's something, it's quite essential to have 0 when x and y are equal, because there is another interpretation in computer science. If you have the same, the same process going on, they have to be dependent, not independent, because you cannot work at the same time.
Yes.
So it's essential to have this.
Yes, and in this context, it says you can't have more than one particle on a
So you
site.
need- you actually need-
Yes.
Maybe
Yeah.
not
No,
here.
I mean, I don't need the definition for this expression, but I'll need it sort of 2 lines further down when I write this in a different way. So it's a natural thing to do. Okay, so Okay, now let's sort of recall what we're doing. So remember that Z is 1 plus some stuff, and we're working in terms of some variables W. But we're interested in log Z. Okay, so right, well, since Z is of the form 1 plus something, we're going to be able to get an expansion of log Z, so to take a Taylor expansion of log Z. And, okay, log Z is going to be the sum Cn W to the n, where everything here is written in terms of multi-indices. Okay, so n is just some sequence of non-negative integers. Okay, so we'll get, so remember it's multivariate, so rather than powers of a single variable, we're getting mixed powers of a collection of variables. Okay, so Taylor expansion looks like this. Okay, this is something that physicists know a lot about. It's called the May expansion. And here the crucial thing for us is going to be that, well, it turns out that these coefficients are all positive. Okay, so this is amazingly useful. So claim all coefficients in the Mayo expansion, okay, more precisely, are non-negative.
Alternating sign.
Sorry, yes. Sorry, yes, I changed variables in my head. Yeah, so they're alternating. So meaning that the sign of Cn is -1 to the
-1.
mod n minus 1. So mod n meaning you count the total degree in all the variables. And it's -1 to the mod n minus 1. Okay, so this is extremely powerful. Let me okay, with one eye on the clock, let me sketch how that arises. Okay, so right, so the first thing is to rewrite this again. So at the moment we're just looking at subsets of X. I'd like to allow the different elements of S to just float independently. So I'd just like to think about placing some vertices down rather than specifically looking at subsets. Okay, so that'll be the sum over n greater than or equal to 0. And now we place n vertices down independently. We're going to get product over product of wxy's and product over I less than j wxi xj. And if you look, that's the same thing as long as you put a 1 over n factorial there, because you can pick your vertices in any order. So what's happening? This enforces that you place your vertices in distinct places, otherwise you get a 0 factor. Okay, so the only non-zero terms in this big sum are the ones where you've placed down a set of vertices on different sites. Okay, furthermore, you must place them on an independent set, otherwise, again, wxi xj will be 0 somewhere. So the only non-zero terms are the ones where you've actually placed your vertices down precisely on an independent set. Okay, and if your independent set has size n, there are n factorial ways of placing your vertices down, so the 1 over n factorial term just ensures that you get the same as before. So you count overall you count each independent set once. Okay. Okay, so right, so we're already sort of able to step back slightly from the graph itself. Now, one way of thinking about this sort of product over I less than j, wx I x j, it's a bit like taking a product over the complete graph. So you're looking at, you placed your n vertices down, you're looking at all pairs of vertices, and there's a nice trick. So if you write wx I x j is 1 plus f x I x j, then this turns into sum over, okay, n greater than equal to 0, sum 1 over n factorial, 1 over x1, xn in x, product wxi, product I less than j, 1 plus f xi xj. Okay, so this, well, this is a sum over all subgraphs. So if you expand out the product 1 plus f xi xj, this turns out to be, well, a sum over all subsets of pairs of the product over those pairs of f xi xj. Okay, so maybe I'll write it down. Sum n greater than equal to 0, 1 over n factorial, sum 1xn, product wxy, so sum over g and gn. I'll write gn for all graphs of order n, so with n vertices. So this is the sum over g and gn, product xi, xj in the edge set of g, f xi, xj. Okay, so in some sense, I mean, you can chase through the algebra, but the point is that what we're doing is we started out with this expression, and we're decomposing it into something that's a sum over graphs. Okay, so I just want to think of this as sum over n greater than equal to 0, 1 over n factorial, sum g in all graphs of something that depends on the graph. Okay, and again, the details come through if you chase it a bit more slowly. Okay, now we're interested in the logarithm of this, and well, this is a sum over all graphs. There's a nice, there's a well, a standard feature that if you have this type of kind of generating function or sum over all graphs and take the logarithm, what you get out is a sum over connected graphs. It's called the exponential formula. So then there's a standard. Instead using the fact this is multiplicative, so log of ZW is, okay, we still get the same sum. Okay, so
Sorry.
yeah.
The sum stuff from 1.
Yes. Okay, so right. So what we've done is we've converted a sum over all graphs to a sum over connected graphs. Okay, and if you expand this sum, then okay. So maybe I don't have time to say this has a very nice combinatorial structure. So it turns out to be a sum over connected graphs, but summing over connected graphs, well, the set of connected graphs has actually, there's a beautiful result called partitionability about connected graphs, which says that you can partition, so the set of connected graphs Cn can be partitioned as a union of Boolean intervals.
Exactly the same partitionability that Roberto was using yesterday.
Okay, good. Okay, so I missed yesterday, so I didn't see this. Okay, so right. So in that case, I'll just say we can use the partitionability here, and so what we end up with is a sum over trees rather than a sum over all graphs. And okay, so you have to look at it a bit. And I don't have time to explain, but because it turns out to be a sum over trees, there's a lot of cancellation or a lot of domination going on. It tells you that the number of edges in the tree determines the sign of that term. Okay, so that's where the n-1 comes from, by the way. So it's the number of edges in the tree. Okay, so through this we get the signs in the Mayer expansion turn out to be alternating. Okay, so what have we got to? So we've got log of z has a Taylor expansion with alternating signs. Okay, so if we, instead of log z, if we change our variables from w to minus w, we have all signs positive. Now, something with Taylor expansion with all signs positive, that's very nice. There's something called the Vivanti-Pringsheim theorem that tells you actually if your Taylor expansion has all signs positive, then the closest singularity to the origin lies in the positive reals. Okay, I hope it's plausible and it's not too difficult to prove actually. Okay, so the same thing works in the multivariate context. And here, well, okay, rather than positive, our coefficients are alternating. That tells us that the closest singularity to the origin lies in the negative reals. Okay, so the closest singularity of log z, or let me just say 0 of z, so the closest 0 of z to the origin, I'll say closest zeros. I'm fudging slightly because it's multivariate, so you have to think about each polydisk separately. Lie in the negative reals. Okay, so I think I tried to do this too quickly, but that's what comes out. Okay, now, so that's the bit that starts from the physics end. You can also start from the combinatorial end. So let me just, again, I'm running out of time, so I'll just say that Shearer had a sort of lovely idea as to what to do. Okay, so suppose I tell you that you've got your bad events, and all you know is the probabilities of the events individually. Okay, what's the worst thing that can happen? Okay, and well, what you want is you want a collection of events that satisfy well, that have the correct dependency graph. And what else? Well, you want them to cover as much of the probability space as possible. So now here's your probability space. You're kind of placing your events down in the probability space. If they are not adjacent to each other, if they're independent, then you know how much they have to overlap. Okay, if they are adjacent to each other, you can choose what you do. Okay, what you want is, okay, well, you're looking for the worst case. You want to cover as much of the space as possible. So you want the probability that none of them happen to be as small as possible. Okay, well, a plausible thing to do is to say, okay, if I'm allowed to, I'll make the events disjoint because I'm covering as much of the space as possible. If I have an independent set, I can't do anything. I know exactly how they have to overlap with each other. Okay, so let's make the probability of intersection x and s ax to be, okay, well, it'll be 0 if s not independent and product of probabilities if it is independent. Okay, this is forced on you because they have to be independent. This you get to choose. Okay, now writing this down, it's not at all clear that it should be possible to do this. So this might not give you a probability distribution, probability measure. I mean, this might not be a legitimate assignment. Okay, but use some work and it turns out that it is. Okay. But if you do this, then you can write out the probability that, I mean, having defined things in this way, provided this gives you a valid assignment of probabilities, you can write out the probability that none of your events happen. Okay, inclusion-exclusion tells you that's going to be 1 minus, well, sigma, just the individual probabilities, plus sigma, well, the pairs. What are we getting? Well, the terms we're getting are minus 1 to the n times, okay, well, the probabilities are 0 if the set's not independent. It's probability of px if the set is independent. We're exactly getting the independent set polynomial coming back again, okay, at minus px. So this is the curious thing. In both problems, we've moved into the negative reals. So here, in order to get a bound on probabilities, we've ended up having a polynomial evaluated at negative reals. In the physics problem, physics context, we started out being interested in what happens in the positive real world. Again, we ended up looking at zeros in the negative reals, as far away as you could be from the positive real world. Okay, but we ended up with exactly the same polynomial, exactly the same locations, and so you can get that they are actually the same problems. You end up, the worst case is the same in both contexts. Okay, that was much more rushed than I wanted, but okay, let me just finish by saying two quick things. So firstly, to reiterate that this was all described in the hardcore context. You can soften everything. And so the nice thing is there's a softened version of de Bruijn's theorem that Alan proved a few years ago. And so you chase through the same argument with soft constraints. Okay, what happens if you try carrying that across to the combinatorial context? Okay, well, now there's a slight problem because you have to think, what exactly in the probabilistic context corresponds to soft interactions. It's going to be something involving weak dependence, and you end up with, you just translate, and you end up with a condition that is a version of the condition in the dependency graph, but a sort of a soft condition. Okay, it's a little tricky to write down, and you get a soft version of the local lemma. So I don't think it's yet found an application, but I think it's possible that it will. So it's nice that you can remove those very hard constraints from the local lemma. You have to be strictly a dependency graph. Maybe that will turn out to be useful. The other piece of traffic is, well, of course, if you're allowed to use any tools you want, then you can get nice results. So a physicist, Todo, looked at zeros of the polynomial of the partition function of the two-dimensional square lattice, and got a non-rigorous result that, okay, the closest zero to the origin, singularity of log z or 0 z, is at minus, well, this very, very precise number. The last number is in brackets because it's not, he's less confident of it. But this gives you a pretty much certainly correct bound on the R of G, where G is a big piece of the square lattice. Okay, so it does actually give something useful to know in combinatorial context as well. Of course, non-rigorously, but that should be the correct answer. Okay, so let me stop there because I'm running over.
It's also amazing that Shearer's result is not so far from the truth. He gets 27 over 256. 0.10 something.
Yes,
And
yes.
this is something like 0.12.
How this compares with critical temperature, this number here?
Well, that's the critical full gas. Oh, compared. This is the critical fugacity on the negative real axis
sorry,
from
this
the
is an
unphysical
H,
singularity.
sure.
But it's incredibly close. I mean, within 20% of the Shearer bound. It's rather rare that a bound in mathematical physics is so close to the truth.
In this Loavsz Local Lemma, it makes sense to think about oriented dependence somehow. You have,
Yes.
you know, there are these versions of Loavsz Lemma. So does
Yes.
it make sense to think about something like that for the Bushin?
I think we talked a little bit about that actually,
I think the answer is we don't know.
and we didn't manage to come up with something natural. But
Right, so I guess the
Yes.
question is, does
it makes sense to think about it certainly.
the independent set polynomial obviously makes no sense for a directed graph. It doesn't see the direction of the graph. But is there some other polynomial naturally associated to directed graphs that reduces to the independent set polynomial if you put in both directions, and which maps to the directed Loavsz problem? Good question.
Well, yesterday we saw this. You know, ribbon graphs and directed graph sounds like something like that. No, so it might be connected with that polynomial.
Depends how you define an independent set in a directed graph. So if you could define it as having no
define it so
directed
that-
circuits.
So there what?
You could define a set of vertices as being independent if it induces no directed circuits.
Circuit.
Let's
Yeah, this is what we were
Circular
discussing.
dimension.
This is what we were discussing, the generating polynomial of acyclic subsets of vertices. And so you proposed that polynomial, and the problem was it looks like the log of that polynomial does not have the standard alternating sign property, but it still might be the right polynomial. I mean, as Alex showed here, the zero free in a polydisk with radii R1 through Rn is equivalent to zero free in the poly intervals from minus Ri to 0. That's what this Avanti-Fring proves. For this acyclic polynomial, those two things are not equivalent, but nevertheless, one of them might be equivalent to the directed Loavsz problem.
You could also
Worth
define
trying.
the set as independent if it contains no directed circuits besides 2. Sorry.
Question here.
Actually, one comment and one question. For the triangular lattice, that number's known exactly. It's about the same. I think it's minus 0.09. It's minus the golden mean to the 5 halves. Actually. Minus the golden mean to the minus 5 halves. But
no, non-rigorously or rigorously?
no, it's exactly the non-rigorous as Baxter. So it's correct. But anyway, is there an analog? You know what offhand what 27 over 256 translates to for the triangular lattice? Or is that 27 over 256?
5 to the 5th over 6 to the 6th. Can you do that in your head?
No. But then a question, does this say anything interesting about if you set Z to be minus 1? Because that turns out, at least from a couple points of view, to have all these curious properties. If you look at the independence complex, Z equals minus 1 comes up because it's the Euler characteristic. And so this has something to do with discrete Morse theory. It also comes up in physics for reasons I won't belabor. But this looks like it might, you could apply all these techniques and then just set Z equals minus 1. So little Z.
Yeah, no.
So it's past your radius here.
Right, yes.
Yeah, past that radius, we basically say nothing.
I'm not quite sure what it would. So in the probabilistic context, I'm not sure what it would mean.
Well, you could still, these
But you
graphical
could just
expansions and all
formally-
that still work.
Yeah.
You know, I mean, all these formulas I think you wrote down, I mean, I mean, the positivity condition won't hold anymore.
But it's past the radius of convergence of the Mayer series.
That's right.
Is the point.
But you can do a Mayer series actually around z equals infinity.
But you want
if
to go
want.
to
You
positive.
can do 1 over z equals 0. Actually, it's inside that radius.
Can I ask you a question? Is this z or w equals -1? Is that special for all graphs or only for the square lattice?
It's particularly weird for the square lattice. It's special probably for many lattices. Actually, if you could find one graph where that was within the radius of convergence, that would be interesting.
So it might be something interesting to say, but I don't see how it would correspond to something natural in the probabilistic context. So I don't think it would carry there at all.
Yeah, there'd be negative probabilities, clearly. But the graphical expansions, I mean, that's sort of beyond all that.
Question?
Yeah.
When you do this trick just behind you for the chromatic polynomial, finish up with the same kind of thing, but I didn't know the second sentence you've written there about, well, I've never seen applied. That statement there, I don't quite understand exactly what it means, but my question is
that one,
yeah,
the partitionability.
Yeah. Has anybody done that? Polynomial case.
The partitionability is explained in your book.
Ah, there you go. I obviously didn't understand what you wrote, but thank you.
Let me a question. If you have a formula for a very particular case, the partition function is very particular that you can make this relation. You make something about the generalization about this, for example, by perturbative extension of the partition function. You have polynomial 1. Maybe it's possible to make this. Yeah? I mean, the result is particular for this problem. What in the non-iterative part of the exclusive volume. But you can generalize this. The question is, can you generalize this by something about expansion of the partition function, by polynomial 1, or it's not possible at all?
I'm not quite sure what you mean, so
Okay.
maybe we could talk afterwards. And
Okay,
yeah.
okay.
In fact, there is a directed graph that is associated to all this, and it does contain the dependency graph. You're just taking vertices to be cliques, and so this will be the vertex set. And the edges, or the arcs, is something really strange, maybe, because it's the so-called Cartier-Fota decomposition, which comes out of the algebraic interpretation of all this. Because you're just taking your events as an alphabet, you take the free monoid and the quotient modulo the relation of commutativity, modulo the independence relation. So you have a free partially commutative monoid, and then there is many normal forms in this case. One of them is the Cartier-Fota, and it can be written down as a directed graph. But now I don't know which polynomial of this directed graph will give you this so-called independence polynomial here. But there exists a directed graph hidden behind.
Okay, so
You're
maybe,
playing with clicks instead of.
yeah, that might be worth thinking about. Yeah. Maybe it's a different topic.